Hello, my name is Nur Christina binti Muhammad Sani. My metric number is 2300557. I will start with introduction for our study. Today we will be presenting an analysis on the performance of power wheelchair on inclined surfaces. Mobility is a fundamental need, especially for individuals with physical impairment, such as the elderly, patients with spinal cord injury, or those recovering from surgery. In this situation, power wheelchair play a critical role in providing safe, stable, and independent transportation, whether at home, in hospital, or in public spaces. While modern design includes smart controls and improved mobility features, one of the key challenges still remains navigating slope or uneven surfaces. Such terrain places extra demand on the wheelchair motor, affecting both comfort and system performance. Now, let's go into the core problem. Although power wheelchairs are built for comfort and efficiency, they tend to struggle significantly on ramp or inclined path. When climbing or descending slope, the motor is forced to output more power. This not only leads to motor strain and increased energy consumption, but also cause faster battery drain, possible overheating, and a general reduction in the lifespan of the system. In addition, users may experience jerky movement or instability, which can pose serious safety risks. Because this issue is so common in real-world environment, we believe it's critical to study and address this limitation. With that in mind, here are the objectives of our study. First, we aim to analyze the forces acting on a power wheelchair as it moves on slope ramp. Next, we will calculate the torque required by the motor at different angles and ramp line. We also want to understand the relationship between slope and motor train, as this can inform us about the mechanical limits and design gap. From this analysis, we hope to propose improvement or safety measure to enhance user experience. Ultimately, our goal is to contribute to the development of the power wheelchair that are more efficient, durable, and safe for inclined travel.
Hello, doctor. My name is Miss Martha with metric number 2406054. Today, I'll be talking about the challenges and solutions related to using electric powered wheelchair or IPWS on an inclined and uneven terrain. While IPWS has transformed mobility for people with physical impairments, they still face major limitations when it comes to slope and road surface. Electric-powered wheelchairs greatly improve mobility for users with physical impairment, but navigating inclined and uneven terrain remains a key challenge. Most IPWS are built to handle slopes up to 6 until 12 degrees. Steeper inclines and low traction surface like gravel or wet pavement can strain motors, drain batteries, and pose safety risk. To improve safety and performance, IPWS often include features like anti-slip wheels, traction control, automatic braking, and adjustable speed settings. However, this system can still fail under extreme conditions, especially if traction is lost. Uh, Technological solutions such as stronger motors, better tires, and intelligent braking system enhance wheelchair function on slopes. User strategies like training on moderate slopes and managing batteries level are also important. Looking ahead, innovations such as real-time terrain detection using sensors and adaptive control systems show promise. This could automatically adjust performance based on the terrain, although issues like cost and sensor reliability still need to be addressed. In short, while IPWS have come a long way, ongoing design and technology improvement are crucial to help users navigate challenging environments more safely and effectively.
Hello, Dr. Chan. My name is Hannah Nadina, now student number 2408664/1, and I will be presenting the methodology for today. So, I will be presenting a comprehensive review of the advancements and limitations of electric powered wheelchairs with a special focus on their performance when navigating inclined surfaces. So, our goal is to highlight key design factors including torque output, center of gravity, traction, braking efficiency, and motor control systems to identify areas for improvement. So first, we start with forces in equilibrium. When the wheelchair is stationary on a ramp, the gravitational component pulls it downslope. We analyze how this is balanced by the normal force and friction to ensure the wheelchair remains stable without unwanted rolling. Second, torque and rotational dynamics are critical. We examine whether the motors can generate enough torque to climb inclines safely without overloading or causing sudden jerks that may destabilize the user. Next, the center of mass and stability analysis looks at how seat position and incline angle affect tipping risk. By adjusting the seat's position, we can optimize the center of gravity for maximum balance during both ascent and descent. Fourth, we analyze load distribution and reaction forces on the front and rear wheels. This ensures the loads are balanced to prevent backward tipping when going uphill or nose diving forward when going downhill. Friction and traction are equally vital. We calculate the required coefficient of friction to maintain grip on different surfaces, especially when they are smooth or wet to avoid dangerous slippage. And then braking dynamics and deceleration come next. We use dynamic principles to evaluate braking torque, stopping distance, and the risk of skidding or forward tipping during sudden stops on slopes. The moment of inertia and wheel acceleration are also considered. We look at how wheel size and mass distribution impact how smoothly and safely the wheelchair can accelerate or decelerate during ramp transitions. Lastly, we assess energy consumption and motor efficiency. We calculate the power needed to climb inclines and explore whether energy can be regenerated during descent to extend battery life. Okay, so now we will discuss the results or the calculations that we did based on the concepts that I discussed earlier during the methodology slide. So before we begin talking about the calculations, I have to discuss the key assumptions that we're making. So basically, I'm using the E degree EW6 ultralight model wheelchair. The wheelchair weighs 14 kg and we are assuming the user to be 80 kg. The ramp angle that we'll be calculating with is 10 degrees. The rear wheels driven by the motors have a 25 centimeter radius and the front casters are smaller. The tires are rubber for grip and the frame is aluminium for lightweight strength. So these are the numbers that we will calculate with. So first, we will discuss the calculation of static equilibrium on an incline. As you can see, I drew a free body diagram. So let's look at the forces when the wheelchair is stationary on a ramp. Imagine the wheelchair on a 10-degree incline. Gravity pulls it downward with a force of approximately 922 newtons. This force splits into two parts. A normal force, which is approximately 908.5 newtons, pressing the wheelchair into the ramp, and a downhill force of approximately 160 newtons trying to make it slide down. So the question is, will it slide? Will the wheelchair slide down? So the rubber tires on dry asphalt provide up to 636 newton of friction. Since we only need 160 newton to hold the wheelchair, it stays put. But warning, on wet ramps, the friction drops to 363 newtons, which is still safe for 10 degrees, but steeper ramps could be risky. So now I will talk about the torque requirements for ascent or the torque needed for the wheelchair to climb. So for a 10-degree ramp, the downhill force is 160 newtons, and to accelerate at 0.5 meter per second square, we need an extra 47 newtons. So the total force that we need is 207 newtons. So the rear wheels, which are 0.25 meters radius, require a force of 207 newtons times 0.25 meters, which will give us a 51.8 newton meter torque or 25.9 newton meter per motor. So the E degree EW6 motors provide 30 newton meter each. So that means they can handle this degree of ramp. But let's say that the ramp goes higher, it would not be able to support. Next, we will talk about the stability or the center of mass. So, will the wheelchair tip over? That depends on the center of mass. Assuming the user's weight is centered 0.8 meters above the ground, the tipping angle is 26.6 degrees, far beyond our 10-degree ramp. So now, braking on descent. Going downhill, brakes must counteract gravity. For a safe descent at 0.5 meter per second square, the downhill force 160 newton, the braking force might be 47 newton, and the total brake, that means that the total braking needed must be 270 207 Newton. So this requires 51.8 Newton meter of braking torque. If the brakes can't deliver this, the wheelchair could speed up uncontrollably or tip forward. Now the traction and friction limits. So the minimum coefficient of friction to prevent slip is 0.18. And since our tires are made of rubber, 0.7, we have a coefficient of 0.7, which is sufficient. But if it is in wet conditions, that coefficient may drop down to 0.4, but it is still safe for a 10-degree ramp. So now the energy and battery life. Climbing ramps drain the battery fast at 207 watts of power. A 240 watt battery like the EW6s lasts just 70 minutes of continuous climbing based on my calculations.
Hello, doctor. My name is Ruqayya Shakir Hussain, matric number 2308432. Today, I will be presenting on the discussion section of this report. So, electric wheelchairs face unique challenges on ramps due to gravity, inertia, and mechanical constraints. This presentation connects our calculations to real world performance and identifies key design limitations. Now, let's look at some concepts in dynamics applied in this presentation. Firstly, Newton's second law in ramp navigation. When going uphill, gravity adds to the force that the motor must overcome. Going downhill, it accelerates the wheelchair unless braking is applied. So both motor and braking systems need precise control to maintain safe movement. Next, work energy principle on descent. Descending a ramp, potential energy converts into kinetic energy. If braking isn't engaged early enough, speed builds up quickly. Regenerative braking systems help manage this energy and even recharge the battery, improving safety and efficiency. We also have torque and angular acceleration. More torque is needed on an incline to overcome both gravity and inertia. If torque isn't controlled smoothly, the wheelchair might slip or jolt. Adaptive motor controllers can help prevent this by regulating torque output. Let's also look at momentum and impulse in braking. So when descending, momentum increases. To stop safely, braking force must be applied over time to avoid skidding. Users with good core strength help absorb this force, but otherwise the braking system carries the full load. We also have dynamic stability and equilibrium. Staying balanced while moving uphill or downhill requires maintaining dynamic equilibrium. A high center of gravity increases tipping risk. Features like anti-rollback wheels and adjustable seats can help stabilize the system. Moving on, let's briefly interpret the results obtained in the previous section. Let's start with friction and traction results. We calculated that at least 160.2 newtons of friction is needed. On dry surfaces, the system provides 636 newtons, more than enough. Even in wet conditions, we still had 363.4 newtons, showing safe traction under typical conditions. Torque and motor performance. Total force uphill was 207.2 newtons, including acceleration. This required 51.8 newton meters of torque total, or 25.9 newton meters per motor. Within the motor's 30 newton meter capacity, that confirms safe uphill operation with some buffer. We also have braking effectiveness on descent. During descent, braking torque needed was also 51.8 newton meters, and the system can handle up to 60 newton meters. So even when heading downhill, braking performance remains safely within limits. Center of mass and stability. Our tipping angle was calculated to be 26.6 degrees, and the ramp is only 10 degrees, leaving a solid 16-degree safety margin. But shifts in posture or added weight can reduce this margin in real life. Battery life and energy use. Power needed for ascent was 207.2 watts. With a 240 watt-hour battery, we estimated 1.16 hours or about 70 minutes of continuous ramp climbing. In real use, battery life depends heavily on how long and how often ramps are used. So overall, we found the wheelchair performs safely on a 10-degree incline under ideal conditions. Motor torque, friction, braking, and stability all meet acceptable limits. Next, let's look at some limitations. Firstly, static friction modeling. We used constant coefficients of frictions in the scenarios considered in this report, which is the wet and dry conditions. Hence, fixed friction values are assumed. However, in reality, friction changes with debris, wear, or moisture. Sudden changes aren't captured in our model. Next, 2D motion assumption. We only modeled motion forward and backward. Real wheelchair use includes turning and side slopes, which affect stability but weren't included here. Thirdly, the braking assumptions. Our braking model assumes immediate and constant force. Real braking has delays and fluctuates with user input and terrain. This may underestimate real stopping distances. Lastly, we have static center of mass. We used a fixed center of mass, but in real use, posture shifts and added loads change weight distribution and can increase tipping risk. In summary, our model confirms the wheelchair performs well under ideal conditions, but safety in real world ramps depends on dynamic terrain, posture, and system condition. Future designs should address these variables. Thank you.
Hi, my name is Muhammad Fahmi Imran, matrix number 220012000. So now, to ensure safer and more efficient powered wheelchair navigation on ramps, several key improvements can be made. First and foremost, the adoption of adaptive braking systems is crucial. These systems can automatically adjust the braking force based on slope, angle, and speed, reducing the risk of skidding and ensuring smooth deceleration during descents. Next, we suggest implementing real-time incline detection using sensors like gyroscopes and also accelerometers. This allows the motor to instantly adjust the torque output based on the slope, improving performance and also safety on changing terrain. Next, we also propose controlled acceleration algorithms that prevent abrupt speed surges during ramp transitions, which these minimize tipping risk and also enhances user comfort, especially for elderly users lah. Next, in terms of energy efficiency, regenerative braking should be introduced. These systems captures kinetic energy during descent and converts it into usable electricity, extending battery life and also reducing motor strain. And lastly, for structural design, a lower center of mass should be prioritized. Adjustable seat systems can dynamically shift the user center of gravity to prevent tipping. Next, to enhance traction, optimized tire design with suitable tread patterns and materials should be considered, ensuring better grip even under wet or uneven conditions. On the modeling side, 3D motion simulations should replace the current 2D model to account for real-world actions like turning or leaning on ramps. We also recommend dynamic friction and braking models that reflect real-world conditions such as terrain irregularities and non-linear brake responses. Moreover, user-specific customization like posture, load variability, and also body characteristics should be included in future designs for better personalized safety and control. Lastly, a collaborative interdisciplinary approach involving engineers, medical professionals, and users themselves will ensure the design improvements are not only technically sound but also practical and user friendly. To conclude, while powered wheelchairs perform safely under controlled ramp conditions, they still face dynamic challenges that flat surfaces don't present. Key factors like torque output, braking strength, and energy efficiency must be carefully tuned to handle slopes effectively. Our study shows that under normal conditions, these systems operate within safe limits. However, for future improvements, it's essential that wheelchair designs include real-time control systems, adaptive braking, and better energy management. This enhancement will ensure safer, more reliable mobility for users in diverse environments.